The race to win wars and explore the stars have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. The nylon stocking. How could a dainty fashion item cause riots? The LED. A tiny light which is helping NASA to explore the stars. The Rowlett-Rutland toaster. What has toast and World War II got in common? We reveal the amazing science and manufacture behind these wicked inventions. Throughout history, humans have developed clothing for practicality, warmth, and to look good. But not as many pieces of clothing have caused a nationwide stir that almost brought down the US post-war economy. Only one of our everyday clothing products has had such an impact: nylon stockings.
At the beginning, stockings was made from silk and from cotton. Till the 18th century, it was worn only by men. And only in the 19th century, the women started to wear stockings. Everything changed in the 20s because of the revolution in fashion, and because of that showing the legs became socially acceptable.
The fabric, however, was not so appealing until 1935, when Wallace Carruthers, a chemist at DuPont Labs, introduced a new, durable alternative to silk: nylon.
It changed everything. By its inventor, it was called as strong as steel and as fine as a spider's web.
This new material proved to be extremely useful. It was tough, strong, waterproof, mold-resistant, fast-drying, and could be spun into fibres. DuPont recognised the enormous potential of this new and exciting material and decided to use it as a clothing fabric. Due to its almost transparent appearance and high durability, the nylon stocking became incredibly popular. They became a fashion statement during the 1940s, with 4 million pairs sold on one day alone. DuPont had created the perfect product for its new material. Then the war broke out.
Nylon was needed during the war, particularly to replace silk, because when the Japanese entered the war, they took over the supply lanes and took over a lot of the supply of silk in Southeast Asia.
DuPont ceased the production of nylon stockings in order to manufacture rope, airplane cords, and parachutes. All over America, the press reported women fighting and pulling each other's hair all over the prized pair of stockings. DuPont managed to regain full production of nylons by March 1946 and started shipping 30 million pairs every month. A popular item worth rioting for, born in a chemist's lab that revolutionized beauty and comfort all over the globe. The nylon stocking is without doubt a wicked invention. The Adrian Tights factory in Poland has been making stockings and tights since 1984.
We have stockings, tights, holds up, knee highs and socks.
The factory uses the latest in modern machinery to design and manufacture high fashion hosiery in a wide range of patterns and colours to the highest quality standard. They are the second largest hosiery factory in Poland, producing almost 1 million pairs of tights and socks per month.
We have fashion collection, maternity collection, plus size collection, wedding, and even collection for a man.
The process of manufacturing tights starts by placing yarn on the stands of the machine. The threads are fed to the cylinder of the machine from 4 different sides. The upper of the tight is made inside the cylinder. Upon a single rotation of the cylinder, 4 rows are formed at a time. The process of manufacturing knitted fabric is fully automated.
Usually the knitting machine contains from 300 to 420 needles.
After approximately 3 minutes, the finished upper is transferred by pneumatic feeder into the bag. One knitting machine can produce approximately 150 to 400 pairs of tights a day. Uppers are checked by stretching them on the control mould. The operator checks whether they are good and looks for potential faults in the fabric. In each production batch, the product parameters are controlled by the gauging device. It checks longitudinal and lateral stretchability of the product, as well as checking that the size conformed to the company's standards. In the subsequent step of the manufacturing process, the toes of the tights are sewn together. The operator puts the product against a tube, which, by means of compressed air, sucks the upper inside. The machine then automatically turns the tights inside out. It then sews the toes of the tights together, after which the product is automatically turned outside in and discharged by the automatic feeder. During an 8-hour shift, a single machine sews together approximately 4,000 pairs of tights. At the next stage of the manufacturing process, the single uppers are slit apart at the top and then made into pairs by sewing 2 uppers together and concurrently sewing in an additional piece of cotton knitted fabric called a gusset, which improves the comfort of the tights. At this stage of the process, the elastic crochet tape is also sewn on.
We still need people in the process of production of tights because of the product. The product is very delicate and we need people to look after the product, to check the quality, because the quality for us is very important, so only people can do it right.
Finished tights are packed into bags and placed in the dyer, a machine that dyes the tights the selected colour. Depending on the colour intensity, the dyeing process takes between 4 and 8 hours. Several randomly selected samples from each batch are taken to the laboratory, where they are tested for conformity to the colour standard in different types of lighting. After the residual moisture has been removed, the process of stabilisation or ironing starts. The operator places the tights on metal moulds, which is then transferred into a high-pressure chamber. After the product leaves the high-pressure chamber, it passes into the drying chamber with a system of infrared radiators. The drying temperature is approximately 90 degrees Celsius. After the stabilisation process, tights are checked and finished manually, for example, by threading on ornamental strings. Next, the product is folded and packed in a film pouch that provides additional protection from damage. The pouches are then placed in decorated cardboard envelopes, which are then labelled with barcodes and information about the model, colour and size. Finished and tested tights are packed into bulk cartons and shipped to customers.
Stockings now are not only accessories, they are the fashion statement on their own right. It's a great challenge for a manufacturer to have a product that will fit for every shape, every silhouette, every size, and also for every function and every occasion.
Lurking behind the latest flat-screen TV at home, illuminating the road, or reminding you that you've left a device on, LEDs, or light-emitting diodes, are the tiny little lamps that are lighting up our world. These tiny bright dots have become a familiar part of our everyday lives, but their connection to pioneering space travel is not so widely known. LEDs were developed in America in the early 1960s and emit light through a phenomenon called electroluminescence, which describes light being produced by a material as an electric current or field passes through it. This scientific behaviour was actually discovered in England over 100 years ago by Henry Joseph Round, but it wasn't until the introduction of the LED in 1962 that electroluminescence had found a commercial use.
An LED is a type of device which has 2 materials sandwiched between another material and one final one on top, which is a glass to protect the materials from decay as electricity is passed through them. You have 2 types of material, an N-type and a P-type, and these 2 materials basically, one allows electrons to move through it and one allows an absence of electrons to move through it. And what happens is When an electron meets in an absence of electron, it drops down into that hole and light is given off of a certain frequency.
The initial LEDs only emitted infrared light that was not visible to the human eye. Think of the little LED on the front of a remote control. But researchers found that by using different materials and compounds changed the light frequency, which in turn translated to different colours emitting from the LED. And soon the race was on to develop semiconductors made from a variety of exotic sounding combinations.
If you make it with gallium and arsenic, so you have a gallium and arsenide compound, or a gallium and nitrogen, you make a gallium nitride compound, each of those can give different colours of light. So you have red, blue and green are the typical colours you make, and blue is actually one of the hardest colours to make. It was finally made in 1994 by a Japanese man, and he used gallium nitride, which was a very hard compound to make, and blue, colours being of a higher energy, is also a harder material to make and make last as long as a red or a green colour.
Pretty colours is where the connection with space travel comes in. Space is vast and space travel lengthy. For instance, it took nearly 3 days for the Apollo missions to reach our nearest cosmic neighbour, the Moon. Mars, our next nearest, would have an estimated travel time of nearly 2 years. So how do you keep your crew fit and healthy for this length of time? Fresh food, that's how. And the development of those little LEDs that you come into contact with every day are being used by NASA to enable future Mars explorers to grow food in the unforgiving vacuum of space.
The best possible use for LEDs in space is to actually grow food. You can provide a continual source of light. You can provide it cheaply. The components are actually very efficient and very reliable. And you can tune them to produce exactly the colours you want.
But why is a constant source of light so important for healthy plant growth? As all school children know, a plant grows by a process called photosynthesis. Plants contain a pigment called chlorophyll that usually gives a plant its characteristic green colour. Chlorophyll captures the sun's energy and uses it to make sugars out of carbon dioxide from the air and water. The sugars fuel a plant's roots, stems and leaves, so the plant can grow, and light is a key ingredient to make this happen. And NASA's pioneering research, which started in the 1980s, has found that it just can't be any type of light.
For growing plants, you often need the UV end of the spectrum, which is the high energy, so the blue lights and anything close to that will actually help plants grow. When NASA used just red lights on wheat as a test to see if they could grow plants in space, they found that the wheat was actually bleached and very sickly, but when they added blue lights or fluorescent tubes at the time, that the extra colour and the extra frequency of lights helped the plants to grow really, really well.
In 2014, the International Space Station started to experiment with growing plants using NASA's Veggie Grow system. The Veggie was comprised of an array of LED lights with pillows that contained the seeds, fertiliser, clay and water that led to healthy lettuce being grown high above the Earth's atmosphere. But NASA's expertise with tuning an LED's colour has not stopped at growing plants. Remember the nasty red LED light? Well, NASA have found a use for that wavelength too. It is called red light therapy and is being used to aid the recovery of a wide variety of conditions by aiding the body's ability to repair itself.
Red light therapy can help repair tissues on a much quicker level by stimulating the circulation, and in turn will increase the chemical messengers called cytokines to stimulate the fibroblasts, which are cells that can help produce collagen and hence repair tissue quicker.
The application of this red light technology is being felt in areas as diverse as pain relief in cancer patients to the treatment of sports injuries and on to anti-aging regimes. So, the next time you use your remote, turn your car headlights on or watch your flat screen TV, the same technology illuminating your world may one day be healing a wound or growing food on a spaceship as it hurtles towards Mars. The LED. Truly a wicked invention. So, how efficient is an LED light? Well, we're going to put it to the test. The experiment. We're going to take a glorious zesty lemon and turn it into a natural battery with enough electric juice to light up our low voltage LED. To begin, we'll need a lemon, actually maybe a few, electric wires with crocodile clips, copper pieces, zinc-coated nails, and finally, our little LED. Next, we gently crush and roll the lemons to release the juice inside. Then, a wire is connected to a piece of copper and another to a zinc-coated nail. The copper and nail are then pushed into each end of the lemon. This process is repeated until we have 3 fruity lemon battery cells. Now, the technical bit. We connect together the wires attached to the copper to the wires linked to the zinc nails to form a chain. We then connect a crocodile clip wire from the last remaining copper end and another crocodile clip wire on the zinc-coated nail at the other end of the chain. Connect the zinc nail to the negative terminal on the LED and the copper nail to the positive terminal, and let there be light. And the science? The energy to power the light does not come from the lemon, but rather a chemical change in zinc as the surface of the galvanized nail starts to dissolve in the juice inside the lemon. This is called oxidization, and the energy release produces electricity. The metals provide the power, and the lemon merely provides an environment where this can happen. Does a fruity future await us? Probably not, as it would take over 6 million lemon cells to create the same power as an average car battery, which demonstrates how energy efficient this little light is. The Rowlett Rutland toaster. Can this humble kitchen appliance really have a military connection? Stay tuned to find out, but first, the potted history of toast. It is thought the Egyptians developed the basic formula for the type of bread we know and love today about 3,000 years ago. But they encountered the same problem that we have today: how to stop bread from quickly going stale.
Historically, when people made bread at home, when you make bread at home today, you'll notice your bread will go staler a lot quicker than the stuff you'll buy in a supermarket, purely because the stuff in the supermarket is pumped full of sugars, but also preservatives. The only way that bread tastes good when it's stale is if you whack it in the toaster, and really there is nothing better than stale bread for the toaster, because it's lost all that moisture anyway. It becomes even crispier and even toastier and even tastier.
Before toasters, toasting was not an exact science, but there is real science behind what makes a perfect platform for your hot, buttery treat.
Scientifically, when we toast bread, we have what's known as the Maillard reaction. That's when amino acids interact with reducing sugars, and they kind of have a bit of a party, and you get all these beautiful tastes and flavours coming out. You get a sweetness from that chemical reaction.
So, what is the military link with a toaster? Rowlett Rutland's founder, Ted Rutland, started making toasters using the same tools that had been making components for tanks during World War II. These toasters also took advantage of some of the war-grade material that was lying obsolete in peacetime.
The first toasters had a large amount of aluminium in them because after the war there was a surplus of high-quality aluminium, which was to make aeroplanes, and so everything was made of aluminium. It became quite cheap.
Rutland toasters have been the power behind the perfect toast since 1947, and they are still going strong today. They are also the proud makers of the king of all toasters, a 6-foot-long, 34-slot monster, which holds the current record for the longest toaster in the world.
We only make toasters to the highest possible standard. We only buy the best switchgear, we only buy the best materials to make our elements with. Everything is perfect, inspected to perfection.
So, how are these shiny marvels made? The manufacture of the toaster's case is the first stage in the process. A sheet of stainless steel is placed into a CNC machine, and the toaster's sides and air vents are punched out to leave all 4 sides as one continuous steel strip. Next, the toaster has its corners formed by the steel strip being precision bent in a machine called a press brake. In press brake forming, the sheet is positioned over the die block, and the die block presses the sheet to form the corner shape. The steel sheet is now starting to resemble the actual toaster, but the sides still need to be connected, and this worker uses an air gun to rivet the sides together. The toaster case is now powder coated to give it a tough and smooth finish. While the toaster case is being finished, the assembly of the internal workings, called the inner screen, can begin. To start, a metal screen with a heat shield and both end panels are riveted together. The toaster's guard wires are then slid into position and the remaining screen lined up over the wires, with another heat shield riveted together to form a metal box. The finger bar, which the toast rests on, and a retaining strip are then fixed onto the bottom of the inner assembly. The next stage is for the heating elements to be inserted into the toaster. The element is a critical part of the toaster, as it needs to provide heat but not melt while in use. The elements are made up of nichrome wires which are wrapped around mica sheets. Mica is a natural silicate mineral and has fantastic heat-resistant properties.
Pure mica, which is mined in big slabs, and then they split it very carefully, and you can split mica right down to just a few microns thick. But it's a pure material. There's nothing added to it at all. There's no silicon or anything in it. And this is punched out into segments to take with serrations along the edge where the nickel chrome iron wire is wound round to give you the correct resistance, the correct amount of heat for that element.
The electrical properties of the 4 elements used in the toaster depend on where they are positioned.
We've got 400 watt elements at the end of the toaster. That's only going to toast one side of the bread, so it's slightly lower in value than the middle elements, which are 500 watt. Finishing with the 400 at this end as well. They're all in. Then we're going to link them together with these copper links.
The inner screen is now finished and can be fixed into the toaster case, which has now had a timer and electric wires fitted. A polished metal cover is carefully placed on top of the toaster and then screwed into place. The toaster is then flipped over and a handle connected to the finger bar to allow the user to manually pop the toast up. The toaster's wires are then connected to the heating elements. The next stage is for the toaster to be checked. To begin, it is carefully checked for scratches, dents, and to make sure all knobs and rivets are in place, and the timer and finger bar operate successfully. The toaster is then given an electrical check, which makes sure all the wires and elements are functioning correctly.
If there's any weaknesses in the elements or the wiring, this will be shown up by an audible alarm. No warning, so that's good.
The toaster is nearly ready. In the packaging area, a bottom plate, crumb drawer, and feet are secured to the underside of the toaster. The toaster is then wrapped and boxed, ready to be sent out to toast lovers the world over.
It's just a design which you can't really improve on. You know, it works, it makes perfect toast. You can't make it any differently. It's just, if it ain't broke, don't fix it, you know.
So there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing background. The nylon stocking, the LED, and the Rowlett Rutland toaster. All wicked inventions.